Hi everyone, my name is Chinmay Sonar. Welcome to my presentation on fair covering of points by balls. This is a joint work with Daniel Lokshtanov, Subhash Suri, and Jishu at University of California, Santa Barbara. I'll move on to the problem statement. In the input, we are given n points in d dimensions. Each point is colored with one of the t colors, and we are given a budget k. Hence, in this example, in 2 dimensions, we are given 10 points colored using 3 colors. The aim is to place k unit radius balls so as to cover maximum number of points such that each color is covered in proportion to its size. Formally, if rho I is the fraction of color class I, that is, points of color I divided by total points in the input, and C star is the total number of points covered by some covering, then we say that the covering is fair if and only if the ratio of number of points covered for color I to the total number of points covered, that is, Ci by C, is equal to rho I. Among all coverings with k unit radius balls, we are looking for a fair covering which has maximum number of points. In this example, we have 10 points, 4 of which are blue, 4 are green, and 2 are brown. Consider the covering in this picture. We have 5 points covered, of which 2 are blue, 2 are green, and 1 is brown point. Hence, this is a fair covering. We define the epsilon fair covering problem analogously, where in the covering budget for each color, we allow a leeway of epsilon factor in upper and lower limit. In this work, we consider the fair covering problem with 2 additional assumptions. First, we consider the disjointness, which entails that balls in the covering must be non-overlapping. Hence, a solution like this is a valid solution for the fair covering problem, but a solution like this is an invalid solution. Next, we consider the discreteness. In this case, in the input, along with the colored set of points, we are given a candidate set of m unit radius balls. And the solution can only choose the balls from this candidate set. Hence, the input to the fair covering problem now looks like this. Now we move on to the motivation for our work. The maximum coverage problem has been studied widely in the literature for its applications in clustering and facility location. Recently, there has been increase in interest for algorithmic fairness. This is because of increase in machine learning algorithms for decision and policy making. In this work, we consider the proportional fairness because proportionality is one of the fundamental and robust notions of the fairness. The geometric max coverage problem has rich literature. In particular, in 2 dimensions, the problem of covering a set of points with a minimum number of disks or covering maximum number of points using k disks is known to be NP hard. The latter problem is known to be W1 hard, which implies that an exact algorithm for this problem will have running time of the form n to the power function of k. Recently, Ahmadian and others, and Beira and others, studied the fair clustering problem when the input is multicolored set of points. Their algorithm computes solution where each cluster has equal representation of colors. Notice that this is a localized definition of fairness which can be restrictive for many real-life applications. In our work, we consider an aggregate fairness. That is, we only want proportional representation for colors in the overall covering. In another line of work, Bandyopadhyay and others studied the colorful k-center problem. Given multicolored set of points, their algorithm computes two approximation of clustering radius when each color only has minimum coverage requirement. In this work, we study a novel geometric max cover problem where proportionality implies both upper and lower limits for each color. We note that having both upper and lower limits significantly increases the complexity of the problem. Now, we summarize our results. Recall that n is the number of input points, m is the size of candidate set of balls, and t is the number of colors. In 1 dimension, with 2 colors, we show that fair covering problem can be solved in time order mn square, and our algorithms take space order mn square. Our dynamic programming algorithm generalizes for higher number of colors with running time order mn to the power t, and it has the same space bound. When the number of colors is large, in particular for omega n colors, we show that the problem is NP-hard. We show a reduction from the well-known exact cover problem. For the higher dimensions, we obtain a PTAS with running time n to the power t, m to the power 1 or epsilon to the power d. In the rest of this talk, we'll sketch the proof of our PTAS. Our PTAS computes an epsilon prime fair covering with 1 minus epsilon times opt many points, where opt is the maximum number of points covered by a fair covering with k balls. Hence, we obtain a bicriteria approximation where one criteria is maximum coverage of points and the other criteria is fairness. We define an intermediate problem named as RB covering. In the RB covering problem, an algorithm computes a minimum cardinality subset of disjoint disk which covers exactly R red and B blue points. Our proof of PTAS has four main parts. First, we show that solving the epsilon RB covering problem is equivalent to solving the epsilon fair covering problem. Note that epsilon RB covering is defined analogously as epsilon fair covering problem, where we allow a leeway of epsilon factor for the coverage of red and blue points. Next, we show how to solve the RB covering problem exactly in a constant size square. Next, we combine the solutions across constant size squares using a dynamic programming procedure. Finally, we use the well-known shifting technique to obtain the PTAS. We describe the details of our algorithms for two dimensions. First, our algorithm computes an epsilon RB covering table CRB that stores the size of an RB covering for all valid RB pairs. The values stored in table CRB are the best values our algorithm can obtain across all shifting partitions. The values are computed using a dynamic programming procedure. Hence, using standard backtracking techniques, one can actually recover the disks which cover exactly R red and B blue points. Values in the tables satisfy following two important properties. First, CRB is at least the size of an optimal RB covering. This trivially follows from the definition of optimal cover. Next, and the important property is as follows. For each RB pair, if there exists an optimal covering which requires K prime disks to cover exactly R red and B blue points, then there exists a nearby pair R star B star such that C R star B star is at most K prime. Now, the notion of nearby is as follows. R star belongs to the range 1 minus epsilon times R to R, and B star belongs to the range 1 minus epsilon times B to B. Once we compute this epsilon RB covering table C, we claim that epsilon fair covering problem can be solved in polynomial time. We say that an RB pair is fair if a covering with R red and B blue points amounts to a proportional solution. Once we compute an epsilon RB covering table C, we iterate through all fair RB pairs and check if there exists a corresponding R star B star pair such that C R star B star is at most K. And after iterating through all such pairs, we return maximum such R star B star pair. It is easy to see that this step can be done in polynomial time because given n points in the input, there can be at most order n RB fair pairs. Consider an optimal fair covering. Let optimal fair covering covers R1 red and B1 blue points. Hence, corresponding to the pair R1 B1, there will exist a pair R1 star B1 star epsilon close to R1 B1 such that C R1 star B1 star is at most K. Hence, our algorithm will return solution which is epsilon close to the optimal solution. It is easy to see that such R star B star covering is epsilon prime fair, where epsilon prime is upper bounded by epsilon. Hence, The epsilon fair covering problem now reduces to computing epsilon RB covering table C. In the rest of this talk, we will see a procedure to compute epsilon RB covering table. We start by partitioning the plane into h by h squares, where h is an integer parameter which is dependent upon the approximation factor epsilon. Let S1 through Sl be the set of non-empty squares. By non-empty, we mean that the square contains at least one of the input points. Since we want a disjoint solution, it is easy to see that each Si can have at most order h square disks. For each such Si and for all valid RB pairs, we compute the minimum number of disks required to cover exactly R red and B blue points such that all the disks are contained inside the square Si. Note that for one such pair RB, we can compute Ri RB in time order m to the power h square since there are m options of choosing the disks and each square can have at most order h square disks. Note that we only consider the solutions in which the disks are entirely contained inside the square Si. Otherwise, if the disks protrude outside the square, then they can cover the points outside the square, and hence the solutions across different squares will not be independent, and we cannot use a simple dynamic programming approach to combine the solution. For a given partition, across the squares S1 through Sl, we combine the solution using a simple dynamic programming procedure where FSRB stores the minimum number of disks required to cover exactly R red and B blue points among first S non-empty squares. Hence, the range of S is from 0 to L. Lastly, we apply the shifting technique, and for each RB pair, we store the best solution in the index RB in table C after iterating through all h square shifting partitions. Such a computed table C gives 12h minus 12 divided by h square fair covering. Due to time constraints, we won't go into the details of this lemma. Since we want epsilon approximation, we want 12h minus 12 divided by h square to be upper bounded by epsilon, which implies that h is of the order of 1 over epsilon. Finally, we do the running time analysis of our algorithm. Computing each RIRB takes n into m to the power h square time, as discussed earlier. Since there can be at most order n non-empty squares, combining the solution with dp for one single partition across non-empty squares takes polynomial time in n and n. Hence, the running time of our algorithm is dominated by the step of computing RIRB. The overall running time of our algorithm is n to the power order 1, m to the power order 1 over epsilon square, since h is order 1 over epsilon. This is as promised at the start of this section. It is easy to see that our approach generalizes for higher dimensions and more number of colors. In conclusion, in this work, we introduce a new geometric fair covering problem. For one dimension, when the number of colors is constant, we show that the fair covering problem can be solved in polynomial time. When the number of colors is large, that is in particular for omega n colors, the problem is NP-hard even in one dimension. For high dimensions, we show a polynomial time approximation scheme. There are several interesting open problems. One is to compute a constant factor approximation significantly faster than our PTAS. Another direction is to consider the general version of fair covering problem, that is, getting rid of the non-disjointness and non-discreteness assumption. With this, I conclude my presentation. Thank you.